Okay, so the first little problem to simplify this expression. So a variety of attempts, some involving log division, which isn't appropriate to this. We can write square root of 8x to the fifth y to the 12th as square root of 4 x to the fourth y to the 12th times the square root of 2x. In other words, I just separated out the 8 into 4 times 2, and the x to the fifth as an x to the fourth times x. Okay, the advantage of this now is I can take the square root of every term here, and the square root is 2x squared y to the 6th. And that goes back to what we've done in class last week. And then that's times the square root of 2x, and there you have it. Now, there's a lot to be learned if we check this. If we square this term, well, I could use the rules for exponents, but people tend to be pretty insecure with those rules. So I simply write this as 2x squared y to the 6th square root of 2x multiplied by 2x squared y to the 6th multiplied by the square root of 2x. And I can group my terms together. I have 2 times 2, which is 4, x squared times x squared. And I'm actually going to write this out a little more completely. I probably don't have room, but let's see if it works out. Okay, the 2 and the 2 I can multiply. X squared times x squared, we can do that. Y to the 6th times y to the 6th. All these things are multiplied, so I can change the order, and I choose this order. And that leaves only the square root of 2x times the square root of 2x. Well, now 2 times 2 is 4. X squared times x squared, what's that mean? X times x multiplied by x times x. That gives you x times x times x times x, or x to the fourth. Of course, your rule of exponents says when you multiply the same base to 2 different powers or to 2 powers, you add those powers. Now, there's a reason for that. People get confused if they don't know the reason. We talked quite a bit about the reason earlier, of course, so you might want to review that. Y to the 6th times y to the 6th. Well, y to the 6th means y times y times y times y times y times y. We could write that out, and then we could write it out again. You'd have a string of 12 y's written out. That's y to the 12th. Okay, so we get y to the 12th. And then the square root of 2x times the square root of 2x is by definition what square root means is that's 2x. Because the square root is the thing you multiply by itself to get that thing inside. So if we multiply the square root of 2x by the square root of 2x, we get 2x. Okay, and now we can write that as 4 times 2 times x to the 4th times y to the 12th. That equals 8x to the 4th, x to the 5th. I left out an x. So basically 2. I got careless, and of course you've never seen me do that before, have you? Okay. That's 4 times 2 times x to the 4th times x times y to the 12th. And that takes care of all the terms up here. 4 times 2 is 8. X to the 4 times X is X to the 5th. Y to the 12th is just Y to the 12th. And now look at what we've got. This expression matches this expression. So we've shown that if we square this thing, we get this, meaning that the square root of this is this thing without the square. Well, that's right here. Now that's something you need to really understand as completely as possible to understand these symbolic manipulations. And all this can be shortcut, of course. You can shortcut it with the rules for exponents. But you want to be sure you understand them, and you want to be sure you can bring it down to this level without really using the rules for exponents. Rules for exponents are shortcut. Okay, if you had y to the 357th, you wouldn't want to write out 357 y's. I didn't even want to write out 6 y's or 12 y's. Okay, but they could have been written out. So we want to be sure we understand that. Okay. Now we've got x squared plus 7x plus 5 equals 0. Now the assignment for today was quadratic formula, I think, or quadratic equations. Okay, and this is recognized as a quadratic equation. It's not linear. A linear equation just have multiples of x and just plain old numbers. It wouldn't have any x squareds. You got x squareds, multiples of x squared, and multiples of x and constant numbers. That constitutes a quadratic equation. And this is in standard form. Form is ax squared plus bx plus c equals 0. So solutions are by the quadratic formula, which I wrote down half of right there, negative b plus or minus the square root of b squared minus 4ac. All that divided by 2a. Now we have to identify a, b, and c. So for this specific equation, which is in this form, I'm going to ask if you can identify a, b, and c. In other words, if I put the right numbers in for a, b, and c, I get this. What are the right numbers? Okay, so, like I said, again, we have this. What numbers do I have to put in for A, B, and C to get this? Got a good answer. Was A equals 1, B equals 7, C equals 5. Okay. Now, you have to put 1 in here. You got 1x squared, which is right as x squared. We know that. And B is 7, so we get 7x. Bx would be 7x. C would be 5. Remember, A is the thing in front of x squared, B is the thing in front of x. It's these are things just not there by themselves. Okay. To give an equation, A is 1, B is 7, C is 5. The solutions are x equals negative 7 plus or minus square root of 7 squared. Everybody wrote that out correctly. And that should be 7 squared there. Okay, negative 7 plus or minus what? Now, one thing I saw was 7 squared minus 20, yeah. And I, okay, well, what's 7 squared? Got the answer, 49. So I'm not sure why that didn't get answered, written down, but as soon as you see that 7 squared, you'll make it 49. Okay? Yep, did that. That was just fun. Okay, so now we get what, -7 plus or minus the square root of 49 minus 20 is 29 divided by 2. So your solution set is -7 plus square root of 29 all divided by 2. -7 minus the square root of 29 all divided by 2. There it is. And sometimes you could write this. Say, or if you wish. This way, because of course, division by 2 distributes over the addition. -7 over 2 plus 29 squared, 29 over 2. -7 over 2 minus the square root of 29 over 2. Sure, that minus nice visible. Okay. There's your solution set. You can always do this with a quadratic equation. The equation of the form ax squared plus bx plus c equals 0. That's it. You can always plug into the equation. Now, there are other ways it can be solved. You might be able to factor these and use the product, the zero product of multiplication, or any number of other things. You can complete the square, which we haven't talked about in this course, which we could have. That there were other things that just demanded more attention. Okay. So that's it. You can always solve the quadratic equation. So let's solve this one. And I'm not sure I want to buy it. It's just kind of. I'm never mind. Yeah. Okay. So what do we do with this? Okay, now if we identify A, B, and C, well, A is 1, B is 2, C is 5. Because we put those numbers into the standard form, we get 1x squared, which is this. We get 2x, which is this. C is 5, so we get C, which is 5. Okay. So x equals -2. As again, it's negative b and b is 2. So we're just putting b in here and here. That's going to be the square root of b squared, which is 2 squared. And then it's -4ac. Well, -4 is always there. A is 1. C is 5. All that's divided by 2a. Since A is 1, that's 2a is 2 times 1. So we have -2 plus or minus the square root of 4 minus 16. All that divided by 2. Okay, well. So again, x equals -2 plus or minus the square root of, and I said 4 minus 16, it's 4 minus 1. two steps at once. Okay, well, that's -2. Plus or minus the square root of, here's my -16. I just wanted to write that down here. It's kind of smudged up. Where you can see it. Okay. So we got that. Now what are we going to do with that? 16 is. Let's see if I can convince myself. Stay on the step that I do. 16, -16 is 16 times -1. I could do the square root of 16. And then we use what we know about the square root of -1, which we've done somewhat earlier in the course. You might need to review that if you don't remember it. But I believe it's reviewed in the section we just did. So it should be easily accessible to you. The square root of 16 is 4, and the square root of -1 is I. This is a complex number. And I is the square root of -1, it's imaginary, that's what the I stands for. This is not a real number, it's a complex number. But now we can divide 2 into both terms of the numerator. We get -1 plus or minus 2i. And the solution set is the set -1 plus 2i, -1 minus 2i. That might seem like a meaningless invention. The idea that the square root of -1 is I, and now we have complex numbers. But the theory of functions of complex variables, you might almost start with the pre-calculus course, but allow complex variables in your f of x equals x squared or whatever function. Well, that theory got developed to such a high level in the 1800s. And by the time I was in graduate school in early 1970s, it was a huge field. And I spent most of my senior year and 2 years of graduate school probing that stuff. Trying to get to the point where I could do meaningful research. Lost the opportunity to do that, and probably wouldn't have been very good at it anyway at the research level. The point is that this is a huge subject, okay? And it's extraordinarily important. We would not have our technological civilization without this. I'll just say that. And it seems that imaginary numbers are in fact real, because at the quantum level, I don't understand this very well, but when you solve the equations of quantum mechanics, these things take on a reality that we can't escape, that we can't work around, that we can't get to any way other than by complex numbers. Now, that's way more than anybody in this course is likely to understand. Let me just say that, at a very high level, these things are essential. So it's not just something somebody made up to make these equations solve. Solutions in many contexts have deep and significant meaning. Okay. And my next class, a physics class, was going to use them to solve some differential equations that govern electromagnetic circuits. Very important stuff. Okay. Okay, just a little bit of function notation. With an example. Let's say f of x equals x squared. Now, this looks like I'm multiplying f by x, but that's not what I'm doing. Okay? This is a definition of the function f. Okay? Now, we want to find f of 6. Well, if we replace x up here with 6, what do we get? Can you write this out? But make all your x's 6. In other words, write out the definition of f, which is this. Here's your definition of f. Write out the definition of f that was x replaced by 6. Let's write that out. Don't copy my words. You only got about 15 minutes. Let's just get cut to the chase. You can always check the video later. Okay, now, but he did that just perfectly. And went back to the definition and replaced all the x's by 6. And you get f of 6 equals 6 squared. Well, now we can then say that f of 6 equals 36, right? Because 6 squared is 36. Okay. Okay, so let's just have a couple more examples. What would you do? Same function. How would you find the expression for f of a plus b? Take a stab at it. You might get it, you might not. Most people do something that doesn't quite work out. Be as literal as you can in your attempt. Okay, now people do all kinds of bizarre things when I ask them for this, and nobody's done it. And it's very good. I like the way this is done. Okay, what do you do? If you got the definition of the function, so you write f of a plus b equals, and then you look at the definition and see what it tells you to do. Definition says that whatever's in parentheses here is going to get squared. Okay, now what's in parentheses? A plus b. Now people go on and say, oh, that's equal to a squared plus b squared, but it's not. Okay, equal to a squared plus 2ab plus b squared. Okay, now pushing you a little bit, but you're doing really well. So let's see. Can you find an expression for this? Carefully using the definition for every expression. Wrote down x plus h squared minus x squared. You already had the x plus h squared when I looked. I was pretty sure you're going to write out minus x squared. Okay. Everybody did a good job of that. Okay, well, I want to expand this just a little more now. And actually, this is very close to the most important definition in first semester calculus, not just pre-calculus. Okay. So it's well worth understanding the function potential. Well, I'm going to say this equals x plus h quantity squared is x squared plus 2xh plus h squared. And you know that if you know the special products. If you don't know the special products, you can do x plus h times x plus h using the distributive law. You really have to be able to do that either way. But especially, you can always go back to the distributive law and use. So once you square the x plus h, you just subtract x squared. What's that leave you with? Write it down. Okay, go ahead and write this down and then say equals what? How does it simplify? Okay, well, we have an x squared and a minus x squared. This just leaves us with 2xh plus h squared. And everybody's doing really well. Everybody got that. Okay. Well. Okay. I'm going to show you the difference quotient. This applies to any function, not just the x squared function, but the x squared function is the one that I like to start with because it's simple enough, but there's some important ideas around it. Okay. Difference quotient is this. F of x plus h minus f of x, all divided by h. So I'm going to ask you if you can write that out and simplify it for this function. And that'll be a good review of a lot of things that we need to do in the course. We've got a couple of minutes to do that. See if you can.